I see that people are continuing to log in, but are there any questions for yesterday's speakers or points of discussion? Also, so I'm the chair of the talks today, so I will plan on following the schedule on the Indicia webpage. So let me know if you believe that schedule is incorrect for some reason. One of the things I wanted to talk about today, I'm particularly curious with regard to the simulations, how the nuclear microphysics people can help you best. What do you need? More equations of state or better neutrino opacities?
For simulations, we need both. I can't think of a priority of either one.
No, of course, yeah. There are now quite a few equation of state tables available. There's the compose effort, which sort of collects them. And I think that that sort of pipeline seems more well developed than in the neutrino side.
And I have a question on the equation of state. So Grant, you were using almost like fits to equations of state. Is that right? You had something that had like a polytropic index, but maybe it was more complicated than a polytropic index. But you had actually form fits to them. How well do those fit the tables? Because certainly those have, that there's an advantage to formula over tables because there is a problem, and I think there's a paper by Doug Sesti a long time ago showing that if you're using a table, you may not conserve entropy if you go up and down on the table, whereas generally if you have a formula that's fitting things, you can ensure that your entropy is conserved. So there's a reason why you might want to have a formula fitting, but if it's missing key physics, then that's bad. And in addition to having a form fitting, that doesn't have the other pieces of physics that we need to do that gives you pressure, but it may not give you the other physics we need to do the calculations. So I was wondering if Grant could tell me, am I off base here? Is there, what should I be thinking along those lines?
Boy, I don't know. I mean, it's computation why we use it, but using a polytropic index seems to work really well. There's a nice paper by Reed that looked at a lot of this. Yeah, what might be missing? We ran into, it's very difficult to do a discontinuity like a first order phase transition with a polytrope or otherwise. You have to smooth it out somehow. Yeah.
But you could do in solids, there's, now I'm forgetting the name, but there's a phase transition formula that is often used when people are using a fit. And that typically was believed to capture, at least and this is different densities, this is solids, planetary densities, but they have these formula for doing phase transitions there. I guess my question, and this is to the equation of state people as well, is how, if we try to do something like that instead of tables, it's not just the numerical advantages, it's actually things like entropy preservation and things like this that having a formula is better for. The question is, are we going to be missing critical physics if we do something like that?
Well, I think it's clear that a sufficiently well-tailored formula should be identical to the table. I mean, I don't think we need to stick to simple polytropes. Maybe it's just a matter of designing the right formula. I don't know about the planetary results, but it seems to me it should be a solvable mathematical problem to replace any table with some analytic function.
Well, segmented polytropes are good because they give you the adiabatic index. So it does have a basis in physics. So,
But yeah, segmented, you mean piecewise continuous?
yeah.
I just worry because they're not differentiable that way.
Yes, you're right. There's a little discontinuity at each time you switch over.
I mean, this is what we do in zero temperature manner, but I know the Oak Ridge group has experimented with, sort of machine learning type approaches.
Oh, well, that's interesting. I should look into that. And also the planetary trick for getting around a first order transition.
Yeah, I'll try and get that during the
Yeah,
talk
I don't-
today. I'll try to track that down. And,
Yeah, I don't know that
and
paper.
put it in.
I'm kind of curious.
I mean, it is something simple, and it may not be good enough. But the problem I have is I don't just need the pressure from the equation state. I get other parameters that I need for my neutrino transport. So the question is, I mean, if you were really having to do this, it's not just getting the pressure, but it's also finding fits for those other quantities that I need to do neutrino transport.
The other quantities you need are, because mostly they're either derivatives or they're like the effective mass, right?
Yeah, there are things like that. Yeah, effective masses and derivatives. And so I guess I would need. I'm not quite sure what I would do. Would I get fits to all of those? I mean, the derivatives. If I have, yeah. The question is, what would I do for all of those to make sure I had the best way of doing it?
Yeah. So I mentioned with regard to the effective mass that this is not so well defined. I mean, even in a non-relativistic model, they quote the Landau mass. In the relativistic model, they quote the Dirac mass. So it's not even the same thing. I'm wondering if it's better, instead of tabulating the effective mass, to just give you consistent neutrino opacities instead.
So Tillotson is I'll put it in the chat, but the equation state that is used in like terrestrial densities for when you have a strong shock and it causes a phase transition. And it's very simple, but it may be something that has the right formula to help do these fits for phase transitions.
One of the things that has scared me, I think Jonah mentioned this, is non-equilibrium effects in mergers, because this is beyond the sort of standard pipeline in terms of generating a table. Is there work on non-equilibrium stuff in mergers, or is he here? Maybe he's not here.
Jonah can correct me. I think he was probably thinking non-equilibrium in the nuclear burning, because it's maybe there's some non-equilibrium in other aspects, but in the supernova field for the longest, we initially put in an NSE and then nothing, and then we had an NSE in a small network and something. And then Ray Hicks has a very detailed nuclear network in his burning. But I maybe, well, I'll let, if Jonah's here, he can say if he was thinking something else was out of equilibrium. There's a scientist here at LANL, Terence Struther, who had looked at out of equilibrium equation of state effects, but if you calculate the timescales, Sanjay Reddy convinced me to go calculate the timescales, and most of them I think would argue that a lot of the the way matter's behaving, most of it is in equilibrium. So the way to figure out if it's bad is to go calculate timescales for equilibration.
Sure.
I'd be surprised if it's something beyond the nuclear burning.
I wanted to ask with regard, because we had a lot of talk on hyperons yesterday, in particular, Debarati and Armin. So how much overlap is there, or how much connection is there between the hyperon models, which you guys and the recent experiments on lambda hypernuclei? My sort of naive impression is that there's a disconnect between, sort of phenomenological models of hyperons and dense matter and, more involved quantum Monte Carlo calculations of hypernuclei.
Mhm. Yeah, I think in our, if I may answer, in our models, the lambda interaction is fitted to the depth of the lambda potential in nuclear matter.
Sure.
So there is
just
there
that
is
single
no
particle
direct
energy
connection. Yeah, at nuclear matter, basically, that's all the information that comes in. We tried some years ago to do hypernuclear calculations for finite nuclei using these mean field type models, and to extract lambda nucleon interaction from that type of calculations. But our current models, this is possible, but our current models don't include this. What is interesting is that, what we found is that there is a very generic type of bracketing of lambda nucleon interaction, in the sense that you need sufficient attraction to produce lambda hypernuclei, but at the same time, if this attraction is too attractive, then you don't get to 2 solar mass neutron stars. So it must be sort of repulsive enough to get heavy enough stars, but at the same time attractive enough to bond lambdas to nucleon. So in that, you can put a range which is determined by these two observations, heavy neutron star nuclei. Right, but I'm not sure if these mean field models are particularly well suited to do, calculations of light hypernuclei. In our case, we tried oxygen and I think calcium, which are medium to heavy. But as you said, there is no connection to high precision lambda hypernuclei calculations via Monte Carlo. That's true. And in case psi minus, there is recent paper by Gall and Friedman, who claim that the potential is not minus 14 but minus 24. So these are typical numbers that we vary for psi minus. And if one accepts that sigma interaction is repulsive, then sigma hyperons become relatively unimportant in this game.
Sure.
So yeah, that's basically what we have. So yeah. And I think another robust thing you can say is that, if you have hyperons, then the mass is much above 2.2 solar masses. So it seems the case in all the models that we consider. So if you think about this 2.5 solar, 2.6 solar mass star, then I think it's incompatible with hyperonization. So this is also something that can be said with high certainty from my point of view, of course.
Mm-hmm.
Yeah. Right.
Is Loic Perot here today? I wanted to. Maybe he's not here. Okay.
And a particular question regarding, changing the effective mass we saw yesterday is the question is if you have such a relativistic density functional and you are changing your effective mass in a range at nuclear saturation density, how the nuclear observables will change with such a change of effective mass. I mean, I suspect that these particular models are fitted a certain effective mass best the nuclear binding energy and RMS radii of neutrons and protons. And once you start changing the effective mass and looking at astrophysics at the same time, the agreement between the model and finite nuclei will be disturbed, in my opinion. So I'm not sure if that's a very good strategy to change the effective mass at nuclear saturation. Because this will spoil the agreement between your model and experiments, basically. In our case, we are modifying the high density behavior or these characteristics of Taylor expansion, which do not affect in any way the low density good agreement between the model and finite nuclei.
So let me, is that directed at Dabarati?
Yeah, it's sort of, yeah. There were other talks about changing the effective mass, so I think
Okay.
I'm a bit concerned, I mean, about this strategy, because again, I mean, changing something at nuclear saturation density will, in your model, will definitely affect your agreement with the experiment, with the fitting of finite nuclei that goes into modeling these density functionals.
Armen, that's a good point. So we did check the charge radii and neutron skin corresponding to these models, and we also did some other tests also, like instead of a flat prior, we changed the prior and so on. But I think the fact was still unchanged, that it was the effective mass which was affecting the F modes the most. So this was quite robust. But like you said, we definitely checked the corresponding observables, like nuclear observables as well as neutron star observables. And the range was not something which was unphysical.
Right, yeah. And still, it's not obvious to me that if you change something, that goes into the protocol of creating these density functionals. Any density, relativistic density functional is fitted to a number of nuclei, maybe more or less. But so once you, and this effective mass is a free parameter that is basically fitted. So once you change your effective mass, there is no way not to change the binding energy, the radii of nuclei, and things like that. So what I was suggesting is that perhaps it's much more effective to fix these numbers which are already fitted, but change the density dependence of your parameters. Like in our case, we mapped it on the characteristics of this expansion, and then through this you change the density dependence of your symmetry energy or energy in general away from a saturation density, and then I think that's more then you don't run into the trouble of modifying your fundamentals, your agreement between the density functional and the nuclear.
You don't have to
just a
necessarily Yeah, I don't think you necessarily have to go that way, and because in principle, of course, there, if you take your covariant model and you fit it to nuclei, there's some, there's some uncertainty in that fit, and in particular, there's some large uncertainty in the effective mass, and then it's just correlated with all of your other parameters, your meson couplings, et cetera, and so. You can just take those new values from the fit to nuclei and then vary the effective mass within that fit, and then you retain your match to nuclei.
Well, I mean, if you change the effective mass, then you have to change also other fit parameters to get the same quality fit, right?
Right, yeah.
Okay, but what they are doing, they are changing only the effective mass, leaving other parameters fixed, like compressibility or, all those things like saturation density or binding energy per particle at saturation. If you fix those and change only your effective mass, you definitively are changing the quality of your fits to finite nuclei. If you change all of them, trying to refit your model, then that's a different story.
As we get closer to the start of today's talks, I just wanted to let everybody know. So I'm just going to follow the schedule on the DCO webpage, and then I will give a 5-minute warning after, so that we after 20 minutes, so that you have 5 minutes left in your talk, and then we'll have another 5 minutes for questions at the end. And I'll just do that verbally in Zoom, unless you have a preference about a particular way you want me to inform you. Okay, that business aside, other questions?
I have a provocative question. After Shinya Wanajo's talk yesterday, his very impressive reanalysis of the neutron star merger light curve. What I would wonder what Shinya would say, he's here, to the statement. Based on this, one could conclude that neutron star mergers are not the source of the R process.
No, I wouldn't say that. So then I agree with roughly speaking, the overall property of the kilonova light curves and color evolutions are in reasonable agreement with the current models. But if you look deeper into details, one problem is so the estimated low mass fraction of lanthanoid that is obviously smaller than what we imagine from the typical solar R process abundances. So then and also as I pointed out, if the light transition elements are highly enhanced, the heating source may not be the R process species, mainly from mass number 130 as expected before, but the main heating sources could be transition species. So then from the point of view of heating rates, the kilonova observation cannot be the proof, a certain proof of the production of R process elements, and also the small estimated lanthanoid fraction. So that may can be explained by let's say we from the observation of metal core stars, we know two different categories. One is the highly R process enhanced stars, well, having the solar type R process pattern, but the other are so-called weak R process or limited R process stars. That show some descending trend of the abundances. having little abundances of heavy R process elements. So then, so I would say still the merger event of GW70 or A70 could be explained by with such kind of a weak R process signatures with very small amount of heavy R process species. So then also so still at least by you using kind of semi self-consistent calculation of the kilonova evolution starting from the merger and long time evolution, still it's not very easy to reproduce the basic nature of the kilonovas. That means the early bright blue emission and the late time dim red emission. So then I just wanted to say I would agree probably the event of the GW70 or A70 maybe our process event, but still we do not have a concrete evidences to say that for now. As I told yesterday. So that's it. So just I wanted to mention we should be more careful to conclude the event of GW70 or A17 is really a typical R process event or not. So that's all.
I agree.
Yeah.
Okay, great. I think it's time. So, and I see we have the first talk up. So Viral Prakash, is that
Yeah.
close?
That is correct.
Yeah. Okay. Are you ready?
Yes, I am. So may I start?
Yes. Okay. I just wanted to say thank you very much, everybody. We'll have Viral Prakash who will talk about signatures of deconfined quark phases in binary neutron star mergers. Thank you very much. And I'll give you the 5-minute warning as usual.
Sure. Thank you. Okay. So good morning, everyone. / good afternoon. First of all, let me begin by thanking the organizers for this, for organizing the ECT Star workshop and giving me the opportunity to speak here. It is a very learning experience. It has been a very good learning experience, especially for an early graduate student like myself. Okay, so today I'll be talking about signatures of deconfined quark phases in binary neutron star mergers. And much of the work which I'll be presenting in the talk is based on this paper, which we announced last month, archive 2106-07885. And this is work done in collaboration with David Radice and collaborators in Jena and universities of Trento, possibly. So let me begin by sort of motivating my talk a little bit. I really don't need to give an introduction to the schematic which I present here, especially to this audience. But just for the beginning, I show you a schematic of the phase diagram of strongly interacting matter. On the y-axis, we have temperature in mega electron volts, and on the x-axis, we have something called as the baryon chemical potential, which we can take it to be as density. So at nominal temperatures and nominal densities, matter as we know it is composed at the most fundamental level, it's composed of quarks in confined states. That is, for example, baryons, we have triplets of confined quarks, and mesons made up of made of doublets of quarks and antiquarks. So, however, it is possible that if you go on to extreme temperatures and densities, these confined states of quarks, they can sort of melt into a phase of deconfined quarks and gluons, sometimes what we call as a quark-gluon plasma. So, for example, if you go up to high temperatures, that is the region at very high temperatures and low densities, these are the regions which are nominally probed by heavy ion collisions, for example, at LHC. And it is here that we have evidences of deconfined quark phases. There is, however, a complementary scenario where we can have ultra high densities, but moderate to low temperatures. where also we can have phases of deconfined quark matter. And it is this region which we expect to be probed by astrophysical scenarios, for example, binary neutron star mergers or core collapse supernovae. So the intention of this talk will be to place neutron star mergers in this picture and to try to justify whether this placement of neutron star mergers is somewhat relevant today or not. And this will provide a useful probes as far as studying, analyzing, and constraining contemporary equation of state models goes. So let me begin by posing the questions. So we assume if binary neutron star mergers, if they do create a deconfined quark phase, we ask the questions, what are the gravitational wave imprints of such a quark phase? How can we probe equation of state models using these mergers? And if there are there any electromagnetic signatures which can provide us a signature of a deconfined quark phase? So how do we go about answering them? We will simulate a range of binary neutron star configurations with two equations of states. And these two equations of state are one which models exclusively hadronic matter, and another one is the one which models the hadronic matter in addition to modeling a first order phase transition to deconfined quark phases. Let me show you these equations of state. This is how they look like in terms of mass radius relationships. So our binary systems here, they are evolved with these two equations of state. B and L are the initials of the scientists who are also authors in our paper, Ignazio Bombassi and Domenico Logoteta. H stands for the equation of state that models exclusively hadronic matter. And Q stands for the equation of state that has the same hadronic treatment, but in addition to that, a treatment for quarks. So essentially you can see that below a mass threshold of about 1.7 solar masses, both of these equations of state are identical. So this means that if you have a neutron star, which is heavier than 1.7 solar masses, it is only here that these two equations of state will start manifesting differences between each other. And so to say, if you have a neutron star defined by BLQ equation of state, and if it's heavier than 1.7 solar mass, it can support a deconfined quark phase in its core. Okay, so a footnote on the kind of code which we are using. We use the whiskey THC code, which is an amalgamation of two whiskey and THC codes. It is, nominally speaking, an extension of THC code to general relativistic spacetimes. And it's the first GR plus hydro code to achieve more than second order convergence in the calculation of gravitational waveforms from BNS mergers. Okay, so let me show you in motion the kind of physics which I'm going to talk about. So here I will show you a visualization of two neutron star mergers. One has been simulated with an equation of state that contains quarks on the left-hand side, and the other one has been simulated with an equation of state that only has hadronic matter. So you will see here that time has a funny label of negative values. So this essentially means this is 13 milliseconds before merger, and the time will reach zero when these stars collapse, when these stars merge, and then it will come positive for the post-merger signal duration. The blue regions that you see here are density regions of 10 to the 14 grams per cc, and the gray regions that you see here are 10 to the 13 grams per cc. So let me run the simulation, and yeah, okay, so this is the in-spiral stage, wherein both of these equations of state predict equal evolution because our masses are below the quark formation threshold. This is the point where the stars merge, and you will be able to see deconfined quark phase appearing in the left panel in red. And it is here that this appearance of quark phase will actually lead to significant changes in the dynamics of the merger. And the significant change which I'm referring to is precisely this particular artifact that you'll see here, that the appearance of quarks will actually compactify the remnant, and it will have an easier collapse to a black hole. So you see that the presence of quarks has actually made the remnant collapse to a black hole, whereas when we had only hadronic matter, the remnant is still rotating and differentially stabilizing itself. And it essentially is a long-lived hypermassive neutron star. So it is this particular premise over which all the signatures which I'm going to talk about will be built. Okay, so let me now move ahead for the gravitational wave signatures. And these differences that we just saw, that is quarks making the remnant collapse to a black hole, on a shorter time scale than a hadronic counterpart is what will be translated in terms of gravitational waves. So what I plot here on the left panel is the gravitational wave evolution. That's the strain plus polarization of the 2-2 mode of the gravitational wave strain. And these two equations of state, the one with the hadrons is in blue, and the one with has quarks is with red. So you can see during the Ames spiral, that is before the time of merging, both of these equations of state predict identical evolution, because both of these essentially model the same stellar material. Now, what happens after merger is that this is when the system probes densities and temperatures in the regions which are favorable for quark production. And it is only in this region where BLQ starts to manifest its differences. And the differences are such that the BLQ equation of state makes this binary collapse to a black hole on a shorter time scale, that is at about 8 milliseconds after merger, but the hadronic remnant still goes on oscillating to become a hypermassive neutron star. So it is this difference in post-merger, which is also very visible if we consider the energy spectrum of this particular signal. So if we consider the energy spectrum, that is the frequency space Fourier transform of this signal, what we find is a characteristic peak frequency, which is a characteristic of many neutron star mergers. And with the appearance of quarks, we see that this characteristic peak frequency gets shifted by a little amount that we call as delta F sub 2. F sub 2 is the name which is used in the literature to refer to these post-merger peak frequencies. So this is not a new thing which we have observed. This is something which was also observed by many other people exploring phase transitions in the context of neutron star mergers. And it was also touted that these shifts in these post-merger peak frequencies are essentially smoking gun evidence of phase transitions in binary neutron star mergers. Well, we also observe such shifts in peak frequency, but we go ahead adding to the story that this may not be a universal signature. That is to say, we will only be able to observe, and as we do, we will only observe shifts in these post-merger peak frequencies for signals which have a substantial length of a post-merger. So what I'm showing you on this two panels is, in the first horizontal panel, I'm showing you different binary neutron stars evolutions with these two equations of state. And the difference between panels as we go from left to right is that we are increasing the mass of the binary and the mass ratio of the binary as we go along. So we see that as we keep on increasing the masses, if we keep on making the binary heavier and heavier, it makes the post-merger evolution shorter and shorter, which is expected because heavier masses are easier to collapse to a black hole upon merger. So as the post-merger length decreases, there is less amount of signal to invert to calculate an energy spectrum. And that is the reason why we observe these two peaks here where there is a significant post-merger, but when the post-merger length shortens, we are not able to make any semblance of a particular F2 peak frequency. And the case is even worse in a case where there is essentially no post-merger. This is a case which we call as prompt collapse, wherein two binary neutron stars merge and there is no intermediate stage form a black hole upon merging. So just to talk about the same signature in an alternative language, these shifts, which were made very explicit by previous works, were also expected to violate quasi-universal relations. So previous works than this work had calculated F2 shifts, the shifts in peak frequencies, and those shifts were so extreme that it was thought, or it was claimed that these shifts would actually violate these universal relations. However, in our simulations, we observed that these shifts are very modest. And with respect to contemporary quasi-universal relations, which you see in the green line here, these shifts are not strong enough to violate them, and these relations are well preserved. Okay, so now let me switch gears and talk a little bit about how can we go about probing the equation of state models, especially in regards to Professor Grant's talk yesterday. I thought that this was something which would be of good interest, and that is why I also started with the premise of probing the phases of QCD with neutron star mergers. So just a little bit background is on what I am about to do is I'll tell you some details about how this BLQ equation of state functions in principle. So what we are doing is we are calculating a quantity y sub q. Y sub q is the quark fraction, essentially the number of deconfined quarks divided by the number of baryons at a particular time in a simulation. And it is a quantity which is dependent upon three parameters in the equation of state. That is density, temperature, and electron fraction, composition dependent equation of state. So a dependence on these three parameters, density, temperature, and electron fraction, means that the phase space of this equation of state is three-dimensional. Okay. However, it is a little difficult to visualize the dynamics of a merger in 3 dimensions. So solely for visualization purposes, what we are doing is we are integrating or averaging over the electron fraction degrees of freedom, and we will be flattening this 3-dimensional phase space to a 2-dimensional phase space solely for a better visualization purposes. And the ranges of these averaging 0 to 0.15 are decided based on the fact that electron fraction near or the electron composition near the core of the remnant will not exceed values greater than 0.15. So this is how we substitute the upper range for these averaging. Now, if I were to plot this quark fraction, average quark fraction, so to say, over densities and temperatures, I'll get a diagram which looks like this. So in the background, what we see here is the phase diagram of the BLQ equation of state. And the colors essentially represent the amount of quarks which are there. So this black phase, this black colored regions represent a hadronic phase where we do not have any quarks. And then these colors progressively indicate the amount of quarks from red to blue as they increase. And the white region here is the pure quark phase where we do not have any hadrons. However, only a phase of deconfined quark matter exists. So this diagram is parameterized by temperature on the y-axis in mega electron volts and density in terms of nuclear saturation density. So over this background plot, you will be able to see that there is a type of a trajectory, a series of points which we have plotted here. Each point, this circles here correspond to one particular point in the neutron star remnant as it evolves in the post-merger. So what I've done is I have color-coded this trajectory of neutron stars. So this is so this is a neutron star as it evolves in the phase space of the in the phase space of the equation of state. So this trajectory has been color-coded with a color that is red for earlier times, green for intermediate times and merger, and blue for late times. So red points essentially means that the star is in the in-spiral phase, and this in-spiral phase lies in the hadronic phase of the equation of state. Now, as time progresses, we have green and blue regions of this trajectory, which are oscillating between a hadronic phase and a mixed quark phase. And then, as Professor Grant mentioned yesterday, that as these neutron stars will go about collapsing into a black hole, they will eventually be found in a mixed quark phase, and that is essentially what we see here in our simulations as well. So this is the point where our code crashes, because that's when we encounter a singularity, the black hole, in our remnants. Okay, so now let me switch gears again and then move towards the final part of my talk. This will be on signatures of electromagnetic counterparts. So in order to compute electromagnetic counterparts from our neutron star simulations, it is important that we record certain properties of the ejecta. So as two neutron stars merge, there is a whole lot of ejecta that is ejected from the remnant and from the surrounding disks. So what we do is we record certain properties, and then we will bin these properties by weighting them against the mass of the ejecta in bins of these properties. So here I show you the ejecta mass histogram distribution with respect to asymptotic velocity and entropy. And it can be seen here that the bulk of the ejecta, which will be in these neutron star mergers, is subrelativistic. It does not go beyond velocities of 0.3 c. However, there is a very minute fraction, about 10 to the minus 4 solar masses, that goes on to highly relativistic speeds, and even more so with the quark equation of state. So to say, the thing to remember is that the ejecta from the quark equation of state in the fast tail is faster in comparison to the hadronic equation of state. Not only is the quark equation of state ejecta faster, it is also more entropic, which means that it is more shock heated in comparison to the hadronic counterpart. We also record distributions with respect to electron fraction and the angular distribution. However, there do not seem to be any robust trends across these things. So apart from the fact that this quark equation of state is a little narrower in angular distribution with respect to the orbital plane. Okay. Another component which can be very useful in deciding what electromagnetic signatures are can be the formation of disks. So here I show you the formation of a disk structure as two neutron stars combined. We define disk as any material, as baryonic material which has density less than 10 to the 13 grams per cc, and it lies outside the apparent horizon of the remnant. And if you integrate the rest mass density over these regions, we essentially have an estimate of the disk masses. So why are disk masses important? Disk masses are important because they will give us a very accurate description of the lifetimes of the remnant. Now, the plot which I show you is a little crowded, so I only want people to focus on these two particular curves, the ones which are colored with maroon, and here I will explain the qualitative difference that's happening here. The solid line is essentially a representative of disk mass evolution, the quantity which we calculated using this integral during a neutron star merger remnant using the hadronic equation of state.
5 minutes.
Thank you. And this dotted lines are essentially the same disk mass evolution with the quark equation of state. Okay, so what happens is, if you see over long time evolutions, this disk mass increases and then starts to saturate and slowly decrease with the hadronic equation of state. Whereas with the quark equation of state, when a black hole was formed, as the black hole forms, this disk starts to get accreted onto the black hole, which is this point of kink, and then a rapid accretion that is visible using this particular slope. So this is the point, the kink, where it appears is the signature where the black hole forms in our simulations. Now, why did I mention these things about ejector properties and disks? It is because these are components in our model which go into calculations of electromagnetic signatures. And I'll show you two electromagnetic signatures. One is for early time kilonova transients, which you see on the screen right now. So what we have is a light curve, a bolometric luminosity as against time, early time from merger, on the order of days to weeks. And what we can see here is that these hadronic equation of state light curves are sort of clumped at the top, these solid curves. And then the quark equation of state light curves decrease in magnitudes as you go on increasing the mass. So this happens because the hadronic equation of state predicts a larger disk mass, and the larger disk mass is essentially a component in one of our, in the model that we use to calculate these kilonova light curves. So to say at early times, we find that quarks or the quark remnants, the quark light curves, the quark transients are dimmer in comparison to hadronic transients. There can be another variant of, there can be another kind of electromagnetic signature that can be late time synchrotron emission, the sort of which is being observed for 1708-17 in X-rays and radio waves. However, here what we find is that the story sort of inverts. For early time, as I showed you, the hadrons were more luminous than quarks. Here, the story inverts to say that the quarks, the quark kilonova afterglows are more luminous in comparison to the hadronic counterparts. And this was the reason, and the reason to this, to the quarks being more luminous is that we observed quarks levying a higher velocity in their ejecta in the fast moving tail. So with this, I will stop my talk and just conclude so that people can have some carry away messages. So there are two kinds of signatures which I talked about. The very first one being gravitational wave signatures. And the gravitational wave signature was the quarks cause an earlier collapse of the remnant to a black hole. And these shifts in post-merger peak frequencies are there, but not always observed. And finally, I talked a little bit very cursorily about electromagnetic signatures, wherein I mentioned that for early time kilonova transients, the quark equation of states produce dimmer transients, whereas for late time synchrotron emissions, the quark equations of state produce brighter afterglows. So with this, I will finish my talk and I'll happily accept questions. I hope I did not overstep the time.
No, you're great. Thank you very much. I think Grant Matthews had a first question.
First of all, great talk. This is fantastic work. I just had one simple question. In the trajectory on the phase diagram, I'm surprised to see that the star pool on the way to a black hole, I would have guessed the opposite. Is this because of the latent heat of the phase transition, or is this neutrino cooling?
So you were mentioning that why does the trajectory go towards the very low end of temperature?
Yeah, as you anything to high density, the temperature goes up. Why,
Yes.
as they're collapsing, unless you
So-
have a cooling mechanism?
Right. So I do not believe it is. These are effects of neutrino cooling. I believe, these 3 points, in my best judgment, are numerical errors, because I believe the black hole is something which forms at this particular point, and then after the formation of a black hole, our code crashes. So we do get points in this white region, but they do not make any sense, because our densities and temperatures, they will blow up as and when we encounter a singularity. So we have manually rejected those points to show only the post-merger probes of the equation of state.
Yeah, it's great. It's a great distinction between a first order and crossover transition. Okay, I'll exit.
Okay, great. Stefan Roswag?
Hi, yes, very, very nice talk. You maybe have said it, but I missed it somehow. You showed these interesting results that with a quark equation of state, you get the larger velocities and more entropies and more shocks. Is there a physically intuitive explanation for that?
So there can be two things, in my opinion. The very first thing can be, with the quark equation of state, the remnant undergoes more violent bounces. And by violent bounces, I mean much more violent oscillations in central density. So with these more violent oscillations in central density, what can happen is the remnant can throw away ejecta at faster and faster speeds. Point number 2 can be, as I showed you in this particular plot here, the frequency of oscillations with remnant increases. So this shifts in post-merger frequencies. These are related to the rotation frequencies of the remnant. And with the quark equation of state, what happens, the remnant is compactified, sort of decreasing the moment of inertia and increasing the angular frequency of rotation. So also centrifugally, the ejecta is thrown at a faster and faster speed. So in my opinion, these can be 2 reasons why we observe faster, these faster tails of velocity with the quark equation of state.
Okay, thank you very much.
Okay, Elias Mos?
Hey, Avira, great talk.
Thank you.
I have one question regarding the spectral frequencies, because you're basically saying that in your case, you do not violate the quasi-universal relations.
Yes.
And the question that I have regarding this is that the case where they were violated, there was an equation of state with a very, very strong phase transition.
Yes.
In other words, if you use those relations that extrapolate what happens at low density and then try to see what happens at high density, in this other case, like the radii of the star changed by several kilometers. If I remember your mass radius curve correctly, that was not the case. So I guess the statement that you wanted to make was more like, it's not that those things could not be detected with the quasi-universal relations, but rather that if you have a mild transition, that they might not show up.
Right. Yes, the point is, as you correctly stated, is that we have a milder transition than those models. That's sort of the differences in the equation of state, which we have used. We have used a new model, which is different from the earlier works. To be specific, Bauswein et al., where they observe these frequency shifts to be violating these universal relations. Another reason for this thing can be differences in the simulation infrastructure that we have. For example, the authors that claimed a violation in universal relations, they mostly used a code that was that considered conformally flat approximations to Einstein's equations and used a smooth particle hydrodynamics code, whereas we use a fully GR code and a grid-based hydrodynamics code. So I think there can be differences in how this phase transition has been modeled, in addition to how we have evolved our systems. And one more point I think which we can make here is that this quasi-universal relation that I show you has or takes into account asymmetric systems as well, using these this symmetric mass ratio. And all these investigations which were done before this thing were mostly on symmetric systems, that is which had mass ratio 1. So this is a more inclusive data set, so to say.
Okay, so maybe one final question from Debarati.
Hey, really nice talk and nice study. I wanted to ask if the equation of state you considered, was it a finite temperature equation of state and you added thermal effects separately or not? And the other thing is, I feel this is a simplified picture just to take a hadronic model and a quark model and with a strong phase transition, because I mean, if I remember other papers which looked at whether there's a prompt phase transition or a delayed phase transition, depending on that, the signal would change. So do you agree that there is more to this story?
Well, we do think that only one way of modeling the phase transition should not suffice. For example, what we have used in the equation of state modeling is a Gibbs construction, wherein we relax the global charge neutrality constraint, and that's why we have a good amount of mixed phase. However, I'm not very well read on Gibbs construction, but that is one way of doing this thing. I'm aware there can be another way of constructing the equation of state, or Maxwell's construction, so to say, wherein we might be investigating different signatures if they exist. So I agree that this is not the only model which can exist. I'm also, to be very sure, very excited about, for example, modeling this hadron to quark phases as a crossover, not just as a phase transition. So this is just, I believe, one of the many ways in which we can do this. And I completely agree with you, there can be multiple ways and seemingly different signatures if you model this phase transitions in a different methodology. Coming to your first question, yes.
So can we, while you answer that, can you go ahead and stop sharing so Carlos can?
Sure. Just a moment, I'll stop sharing. And just for your first question, Debarati, yes, this the very first equation of state in this context that came was BL, the T equal to 0 US, for which I showed you the mass radius relationship. It was modified in two ways. First, we added a thermal component, and that was used in certain papers. However, then we extended it to a finite temperature equation of state with finite proton fractions and electron fractions. And that is what we use here. And that is what we call as the BLH equation of state.
Okay, great. Well, thank you very much. Excellent talk. Let's go ahead and move directly on to Carlos Bertolani, who will talk about neutron tunneling in neutron stars, magnetars, and neutron star mergers. Thank you very much, Carlos.
Oh, okay. Thank you very much, Andrew, Rebecca, Chris, for the invitation. It's a great opportunity to talk to the experts here. This is a work I have done in collaboration with Ronaldo Lobato. We are both in Texas A&M Commerce. I am going to talk about neutron tunneling in neutron stars, magnetars, and neutron stars mergers. I thought that the length of this talk was like 25 minutes. This is the first time I'm talking about it, so I hope I use up the time I have. If not, you have more time for questions. So I came to this business because this is a very interesting subject. These fast radio bursts, they were first observed in 2007. And these are radio bursts with duration, the width of the duration of, it's like between 20 microseconds and 20 milliseconds. But they have been found to release a huge amount of energy, of about 10 to 38 to 10 to 46 ergs per second. So what are the things? We don't really know. And I was surprised recently, like a month ago, that the observed ones were about 60 or 70. And last month, it grew by a factor, a huge factor. So this CHIME observatory in Canada observed about 500 of them. So just, I knew about this just last month. But they are still unknown. Nobody really knows how they are formed. So one of the things that we know is that from these numbers here, this width here, we can find what is the size of the engine which produces these bursts. And taking a value from this range here, we find that they have to be about 10 kilometers. So it's probably coming from a neutron star. The other thing that's observed about this fast radio bursts is that there is only a few of them who are repeaters. They repeat, which is about a fraction of this 600, a factor of 1/10 or so of the 600 or 700 maybe that exist. They are observed by now. So they have also some waiting point. So the repeaters, they repeat, but then there is a quiescent time in which about 5 days or even larger in which the repetition occurs. They have been found to have a radiation which is very narrow beamed and polarized. So this leads to the conclusion that probably they are also coming from magnetars. So they also have gigantic source temperatures of 10 to the 36 Kelvin. And this also points probably to magnetars because this would be a coherent radiation which increases with the square of the number of particles, mainly, as we know, other models have electrons in magnetic fields providing this radiation. So the conclusion, the fact is that most of the theoretical models that predict the existence of these fast radio bursts are linked to magnetars. Okay, so it must be something which is associated with the structure of the neutron star itself, together with the magnetic field, a strong magnetic field. So here is a model. This is a popular model which was based on the study of this FRB 121102, which is a repetitive FRB and has been studied in detail since what was first found in 2012 or so. So in this model here, you have a magnetar and you have a flare, and the flare, it releases electrons and other charged particles which collide with previous remnants for a previous flare, okay? And they create a huge magnetic field because these are charged particles. So this magnetic field with the charged particles, they create then a shock wave, which is responsible for the fast radio burst. So this is a popular model. It's based on this repetitive FRB, but we don't really know if this is the case for explaining this phenomenon. Now, there is also other models. For example, another popular model used magnetic field, and as you know, you can have often waves from these magnetic fields, which, for example, in the sun is responsible for the much larger temperature in the corona than at the surface. And these alpha waves, they, from electrons expelled from, are created by the strong fields. They can, a crustal quake in these magnetars can create large amplitude alpha waves, which go from inside to the outside of these regions, and also producing E plus E minus pairs, which are clumped into currents like that, and they clump into E plus E minus in clumps here, which are responsible for emission of powerful coherent radiation. So this is another model from this group here. Other studies of this repetitive FRB have observed that this waiting time that I talked about previously is a fact from observation from FRBs. If it comes from magnetic fields or waves coming from inside of the the neutron star, it leads to magnetohydrodynamic instabilities, which do not have, in fact, correlation with the waiting times. And they should be non-episodic. They occur from times to times, but no real repetition this for the waiting times. And they should be related to the density in the neutron star and the size through which the wave propagates within the neutron star and to the magnetic field. And by doing this calculation here, this is the radius of the star, this is the radius of the crust. Inserting here, it's compatible with the waiting times observed in FRBs. So what we propose is the following. If I come back here, I wrote here that there are as many theory models as observations, right? So at the time we had about 60, 70 theory models in this. Now the observation increased the number of FRBs to 500 or so. So I think the number of theory models are much smaller now, but at the time that I was thinking about this, it was a very large number of theory models. So what I have just shown you is just a few of the models that people have thought. There are people who think that this FRBs come from merging of neutron stars. So, and so on, so cataclysmic processes. We propose a different thing. We propose something which comes from nuclear physics directly, which is neutron tunneling. Our idea is the following. Something happens to the neutron star. So like crust fracture, which can lead to elastic waves propagating in the crust and can lead then to inhomogeneities, where you have more neutrons packed in a smaller space and voids of neutrons in nuclei, which can then migrate to other nuclei by tunneling, because neutrons tunnel much easier than protons, right? So the idea is that we could have some cataclysmic process like crust fracture or star quakes, which go into compressive waves, which go to neutron concentrations at some points and voids. And at these regions, the neutrons would flow, and when they flow, they tunnel, they go to different states, and they will emit radiation, gamma, or even beta decay, and emit electrons, which can be part of the process releasing energy in the magnetars, okay? So each tunneling process should release at least like 1 MeV of the order of 1 MeV. And when you count all of them, you can really have a huge energy release, as I will try to show you. So what we wanted to do is a three-dimensional model, as you have done in many of your calculations out there. But I'm not yet there, so instead of doing a three-dimensional model, in which I look for diffusion and the energy release by diffusion from these neutron inhomogeneities or nuclei between releasing the neutron between themselves, what we did is a one-dimensional model. But a one-dimensional model should give us a lot of insight, as we have learned from many areas of physics, like, well, I do not know, solid-state physics. We have learned a lot from the Ising model or Hubbard models. These are one-dimensional models which have given a lot of insight in physics, and that's what we want to know. We just don't want to calculate things and get results and do not know what they are. We want to have insight on the physics, right? So I hope that this gives us the right insight, and let's see the consequences. The consequences are the following. Here I have a one-dimensional inhomogeneous model, density model, in which these are pockets where you have lots of nucleons. I will consider only neutrons, because in the end, even if this is a nucleus, this will be a very rich, neutron-rich nucleus. And basically what will happen is that the neutrons will tunnel. So the protons will be basically remaining in these pockets. So our model considers pockets or inhomogeneities of neutrons, and they can tunnel between these wells, okay, these regions, either individually or they can transfer by pairs. Okay, so in a one-dimensional lattice would have situations which have densities like that. In fact, we did simpler than that, but that's the one-dimensional model that I want to do. Okay, so the questions that we are going to ask from these exercises. Does this energy rearrangement, which occurs when the neutron goes from here to here, there is some rearrangement in this system here. Does this rearrangement affect tunneling? We know it does, but we still have to do the calculation to see how. So do the neutrons transfer in pairs or individually? Okay, so there is some previous calculation showing that the tunneling of pairs is enhanced because of the pairing property, like in Cooper pairs, for example. So do these pairs break up during tunneling? This is another interesting question. And do we have to do a non-perturbative calculation, like a time-dependent calculation? It seems so, and I will try to convince that this is true. And assuming that now we understand this tunneling problem of neutrons, if this is understood, could be that they would power a fast ray bursts, soft gamma ray repeaters, or anomaly X-ray pulsars. I think they could. I'll try to show you. Let me go back and assume that we have a system of atoms, for example. We have looked at this before, a system of molecules. And the beautiful thing in atomic physics nowadays in quantum optics is that they can create the systems in the laboratory. They can put lasers, they make interferometry. So they can create these wells here, and they can confine atoms within a certain pocket. And here what we have done, we have made a simple study, but it's very transparent, and we learn a lot of physics out of it, in which you put molecules here, and then you ask yourself, how quick do these molecules move by tunneling to neighboring sites? And how do they fragment into atoms? And how would the atoms, by their way, move from these sites to another site? This seems to be a very simple problem. And you see, this is the equation that we need to solve here, which is almost trivial, right? So we have only two coordinates, the coordinates of the two atoms, 1 and 2, plus the mean field, that this is the optical lattice, and the interaction between them. And then we have to put this in a time-dependent Schrödinger equation and solve it. But it yields some complexity, which shows that, for example, dynamical Hubbard models, which are used in many papers in Nature and so on to describe this problem in propagation of molecules in optical lattice, is not really well based. We have observed a lot of interesting phenomena. For example, the molecules can break, dissociate into atoms, which will tunnel individually, and they can also by themselves tunnel, and the time dispersion, how they propagate, is very different. And I'll show you in this figure here. You see, this is the average location of the molecules. I will not enter into the details of numbers and everything else, but only the physics here. What we did is we transformed this problem into a diffusion equation, and we got that this quantity here, which is associated, and in fact, I cannot see my, let's see here, sorry, I am in front of my, I have you guys in front of my transparency, so I cannot read my transparency. But I will show you that the thing is that this coefficient here is related to the initial location of the molecules, this confining of the initial molecules. So as expected from solving this equation here, asymptotically, you get a result which is non-trivial. There is a transient time, but at very large times, it goes what we expect from the diffusion equation. But it also has some quantum mechanical aspects in which this dispersion depends on the localization of the molecules in the beginning. In fact, this is expected, but all these square roots and powers, they are not trivially coming out. Now, for the atoms, we see a completely different picture, you see? So it's a completely non-trivial behavior of this system here. So you see that the one-dimensional models, they give us insight of things that have been very useful in physics. And for example, by looking at these simple situations like that, you have two particles interacting in the tunnel, you have so many problems, you have so many things like your iPhones and everything else uses some of these effects like resonant tunneling, you know about Feshbach resonances, and you know about situations in which the molecules can be broken up, dissociate, and they can recombine too. And in fact, another thing which is very interesting is that if you have a Cooper pair and it tunnels, it's very, very resilient to breaking. Although Cooper pairs are some things which are very fragile, they are resilient to tunneling, which is also shown in this article here, which is also very interesting. Okay, so let's go to my problem now with the neutron tunneling. My problem is a one-dimensional problem, so I have a lattice which has a certain size. I discretize the lattice. I have a second derivative, which is also taken in terms of differences between neighboring points. I have a mean field, but if I want to include a calculation which has pairing included, then I have to use this U's and V's associated with quasi-particles, and I have the density matrix coming from the U's, the V's, and I have pairing density matrix coming from the V's, and I also have other things like pair correlation density and the interaction density. If I take pairing out, then this would become what we know by Hartree-Fock time-dependent Hartree-Fock calculation, right? So this is called a time-dependent Hartree-Fock-Bogoliubov in one dimension. So how do we prepare the neutrons? How do we confine them? As I said, it could be applied to nuclei too. I'm talking about neutrons because I know that the neutrons are the ones who are going to tunnel. So we prepare them initially in this mean field together with the interaction between them, and then I force them to be confined with a harmonic oscillator, okay, a parabolic potential. And here, so the lambda, this lambda here and the parabolic potential is adjusted so that I have a small valence neutron binding. So I expect that if I have this phenomenon occurring in stars, this nuclei will not be very bound. So the neutrons will be loosely bound and they can migrate from one pocket to another, one in homogeneity to another. So I change this number so that as I increase, and here is the systems that we have studied more frequently, they contain 20, 40, 80, 160 neutrons. And then the calculation becomes very, very time consuming, and we only did for a few cases for larger values.
Okay, I'm sorry, I lost a little bit of track. 4 minutes left.
I have 4 minutes.
Yes.
Okay, so to calculate the time evolution, instead of using the diffusion equation, we in practice used a simpler mechanism. We just took the the rate at which the neutrons are going out of certain impurities. Okay, and this is what we got. So this is the rate at which you can think about this diffusion rate, is the rate at which the neutrons are leaving the regions where they are more densely packed. And this is the separation energy here of one neutron. And as expected, this will increase as the separation energy of the neutron decreases, and also with the number of particles, right? But it's far from trivial because there are interferences. This is a quantum mechanics problem. And so there is no resemblance to perturbative models. So if we switch off pairing, that's what happens. We have here, if we switch off the neutron-neutron interaction, this is what happens. We have here the results for this diffusion rate without the interaction between the particles. So the interaction between the particles play a large role, as you can see. So it increases the rate by a factor of 5, okay? So with no interaction. So this is expected because you have this glue between the particles. We tend to keep them together and not go away from those pockets. So if we set the Perry density equal to 0, then we have some sort of surprise, which is unexpected, because I would expect that pairing would enhance tunneling, but it doesn't enhance so much as I change here. It's almost like the numerical error that we have. In fact, these are numerical errors here. So not numerical errors, but the average over time up to a point in which this becomes very late times, there is a transition to more neutron coming through the barriers. So we compare to perturbative calculations like simple WKB, one dimension, and we found out that there are large differences. So which points to the fact that if one is to study this problem seriously, one needs to do complex three-dimensional calculations. Not perturbative models will not work so well. So our model is basic. So here I also show that if I go to very large number of particles, I have what more or less I expect. There is a reduction because these particles, they like to clump together because of the force, strong interaction. So there are some obvious things which emerge. So the basically model that we have is that I already explained before in the neutron star. So let me go to this burst due to tunneling, right? So if I want to calculate the total energy of a burst due to tunneling, I would have to have average energy due to tunneling. Only the valence nucleons will tunnel. The ones below in these pockets will not, because of Pauli blocking in the other regions. So the valence neutrons are the ones who are probably tunneling. So it's about 1 MeV. Let's assume that. I have the number of impurities, which I don't really know. I will show you how I calculate it. And then I have to integrate over time, which means, so if this is an elastic wave, this is what determines this time here is the time that it propagates through one space to another. And if I assume 1/100th of the speed of light, so this time should be related to distance of 2 kilometers and this here. So, so I allow also alpha D is I make the clumps very large with alpha. I can make while D is the distance between them. Okay, so
can we get close to the end? Yeah, okay.
Yeah, Andrew, I'm almost finishing. So
okay,
what
great.
we did, sorry?
No, that's great. Keep going.
Yeah, I'll conclude. What we did, we calculate this number of impurities, okay, by using a cylindrical cap around the lines of the magnetic field at the pole of the star. And we considered the rotational frequency and also the possibility that you have twisted fields. Okay, so with this is the last figure I will show. We have that as a function of the distance between these inhomogeneities, we can find values below, let's say, 50 Fermis between them, in which the energy released is really large. It enters this region of the observed FRBs. Okay, so with that I will conclude and say that this could also play a role in neutron star mergers, because you form also inhomogeneities as they merge, and this probably is a phenomenon that will occur there and might release also a large amount of energy by neutron tunneling. Sorry for going over.
No, that's okay. Just a few quick questions. Anyone?
So
if not, sorry, Arne, go ahead.
Yeah, is the energy released at the surface of a neutron star, or are you thinking about inner crust where we have free neutrons?
Well, this will go into gammas and beta decay, the energy when the tunneling occurs. So it will come from the crust, very probably. Yeah, that's the model that we have. So it's
So if you are generating heat, I mean, then basically neutrinos will quickly take it away. I mean, why it should propagate as electromagnetic radiation through the crust and go out into the free space?
But these neutrons, they go to states which are unoccupied. And
that's fine. That's fine.
Yeah,
but
by
neutrons...
decaying to other states, they will emit gammas, probably.
So Carlos, go ahead and stop sharing, and then we'll while we continue just the discussion for 1 minute. And Janos,
Yeah,
can
sure.
you?
Let me see here. Stop sharing. Yeah. So who was asking this question?
That was Armin Sadrakian.
So you don't believe that the gammas can be produced and carry away radiation?
No, I'm just asking about the details of the model. It was not clear. Are you creating this on the surface of the star or inside it?
No, this neutron tunneling has to occur where there is neutrons. It has to.
That's okay. Then it's if in inner crust, then you have to transport this radiation through the crust.
Right.
And photons are usually opaque. They have short mean-free path. So if you are generating gammas, you have to somehow transport them. You have to show that.
So the opacity will also lead to if this is a lot of photons, they also lead to compression waves, which in the end will also maybe even lead to the fracture of the crust. So if you have such amount of energy being released at once, it might be the reason for this burst. Why not? Okay,
so let's go ahead and we'll finish the rest of the discussion on that tomorrow. We have our next talk. Can you pronounce your name for me, sir?
Yeah, I'm Janos Takács.
Janos Takács. Okay. Please go ahead. I will give you a 5-minute warning. Thank you very much.
Right.
And my apologies to everybody because I see I've actually messed up the schedule a little bit. I'll try to fix it. Yes. Thank you so much.
All right. So hi, everyone. First of all, I would like to thank the organizers for the opportunity to present here. I am Janos Takács, and I am a PhD student currently working at the Wigner Research Center for Physics. My PhD supervisor is Péter Kovács, and currently we are also collaborating with Professor Jürgen Schaffner-Billig from Frankfurt. So what I would like to talk about is hybrid stars, and specifically the quark matter inside them. And so I will concentrate more on the quark equation of state and the field theoretical part. So I hope it will be understandable for everyone. So let me just start with a brief motivation. Here is a figure that you've already seen now a couple of times about the phase diagram of QCD. And what's important here is that we may use different types of methods to try to map this phase diagram. For example, we can try to solve QCD exactly by lattice calculation, but then we get to the problem at higher densities that there is the Stein problem, which hinders us from solving it at higher densities. And we can also use heavy ion experiments. For example, the FAIR and NICA experiments are some of the heavy ion experiments that will be finished in the near future and which will provide us with new data in the high density region. And of course, we might also use neutron star observations. That's what we are here for. And coming from lattice calculations, instead of lattice calculations, we might resort to phenomenological model. But what we do not have to go directly to completely phenomenological models. What we can use instead is effective models, which are still microscopic models, but with some degrees of freedom integrated out. And the useful part of that is that we may try to compare our effective models at a finite temperature and low density with lattice calculations, and then we may try to extrapolate the results to higher densities as well. So so let me just go through an introduction to chiral field theories, which might be useful for people who are solely in the field of astrophysics. So what you can see here is the QCD Lagrangian. It has a quark field and also the gauge field part. And by construction, it has a local SU3 color gauge symmetry. But if we look further, then we can find other symmetries as well. For example, if we project the quark fields to a left-handed field and the right-handed field, then we can see what happens to the terms in the Lagrangian. So first of all, we have the kinetic term, and that basically separates to a left-handed part and the right-handed part. But the mass term, it does not separate into these parts. It will have mixed parts between the two fields. But while we can say that the masses, quark masses, are quite low, they are of a few MeVs, and they are quite low compared to the dynamical scale of QCD, and well, therefore we can say that they are negligible from our point of view. And then we have an additional symmetry, a chiral symmetry, which is a U3 left times U3 right symmetry, which is also equivalent with a U3 vector times U3 axial global symmetry. All right, it's fine that we have this symmetry, but we would not have any structure if we only had the symmetry. So to have a structure and different meson masses, we need to have a symmetry breaking process as well. So we can look into the different symmetry breakings and what these produce. So first of all, there is a spontaneous symmetry breaking by the QCD vacuum, and these would create Goldstone bosons, so massless bosons, which are the pseudoscalar mesons, such as the pion. But because we also have explicit symmetry breaking by the quark masses, then the SU3 axial symmetry will be broken, and then the pseudoscalar mesons will have non-zero masses. And we can go further than that by saying that, all right, the quark masses are also not equal, then the U3 vector symmetry will also be broken down. And what we would be left with is a U1 axial symmetry and the U1 vector symmetry, from which the axial symmetry is also broken due to the 't Hooft-Instanton mechanism, which produces the unexpectedly large mass of the eta prime meson. And what we are left with then is the U1 vector symmetry, which corresponds to baryon number conservation and which is not broken, therefore. All right, so then how can we model these symmetries? How can we put it inside a simple model? So what we can use basically the simplest model is an SU1 linear sigma model, which contains quarks and mesons. So the gluon fields, these degrees of freedom are integrated out. And the Lagrangian that you can see here is of the linear sigma model. And it has a quark part, also a single scalar and a single pseudoscalar meson with kinetic terms. And these mesons also couple to the quark field. And these mesons also have a potential term which has a non-trivial minimum. And because of this non-trivial minimum, this will produce spontaneous symmetry breaking. And by this spontaneous symmetry breaking, the quark mass, for example, will be produced, and also we will have the Goldstone boson, the pion with 0 mass, and of course the sigma meson mass will also be generated therefore. And what's important to note here is that by looking at the masses, then we can somehow try to fix the parameters of our model to reproduce these masses correctly. And also, if we go forward and we consider thermal environments where quantum fluctuations are also present, then at large temperatures, what we will see is that the sigma condensate will go to 0, it will vanish, and therefore the chiral symmetry will be restored. So this is the basic idea behind linear sigma models and also more complicated ones. And the SU3 counterparts of these models are actually quite successful in describing vacuum phenomenology and also the behavior at finite temperature. So now let me move on to our model, which is the extended linear sigma model, and this is an SU3 model, so with 3 quark degrees of freedom. So instead of having only a single scalar and a pseudoscalar meson, we have here the complete non-nets of scalar and pseudoscalar mesons, but in addition, we also have the axial and vector meson non-nets as well. And what you can see here in these matrices is the particle content of these non-nets. And basically the fields here correspond to specific particles, and the assignment of particles is obvious in most of the cases, except for the scalar sector, in which the problem arises where if we look at the particle data group booklet, then we will have more scalar particles there than what would fit into a single non-net. So these are probably mixed states of diquarks and tetraquarks and so on, but what we consider here are only diquarks. So, and also here we consider spontaneous symmetry breaking, which is due to a non-strange and a strange scalar condensate. So let me move on to our Lagrangian, which is here and which might look a bit complicated, but what is important to tell you about this Lagrangian is that it contains basically the most general terms up to a certain order of the mesonic fields, and while the first four rows are the mesonic terms, and the terms colored with red and blue are the explicit symmetry breaking terms. And also in the 4th row, there are mixed terms between the scalar and vector sectors, which is well important also in our model, but which can rarely be found in other models. And also in the 5th row, there are the quark terms, and these quarks are also coupled to the mesonic fields. Another important ingredient of our model are the Polyakov loop variables. These variables basically correspond to the gluonic fields, and these are some effective variables, and they are the fields that are responsible for the deconfinement phase transition. So basically what they do is that they modify the Fermi-Dirac distribution, and that's how they are responsible for the deconfinement. All right, So now let's talk about how we determine the parameters of this model. As I mentioned before, in the simple example, we can use basically vacuum phenomenology to fix parameters. For example, we might use different mesonic masses, and that's what we do. We use 16 physical quantities for this. And but in addition, we also use decay lists of different mesons, which we get from 3-point functions. And what we also want to do is that we want to recreate the finite temperature behavior at zero chemical potential. So we also fix the pseudo-critical temperature to the lattice value. And what we do then is that we calculate these quantities from our model, and we basically compare them to the data from the particle data group booklet. We then use a chi-square fit, and then what we get are matches within a few percent, basically. Except there are only a few deviations, larger deviations. One of them being that we get very low masses for the lowest mass scalar mesons, which is a feature of our model. So then we might also investigate the finite temperature behavior of our model. We can compare the results to the lattice simulation results, and this is what I show here. On the top left figure, you can see the subtracted chiral condensate as a function of temperature. This subtracted chiral condensate is what signals the chiral phase transition. And the different colored lines correspond to different critical gluon temperature, and this critical gluon temperature is a parameter of the Polyakov loop potential. But basically what you can see here is that we get a pretty good fit with the lattice results. Also on the bottom right, what you can see is the equation of state at zero chemical potential. So what is shown there is the reduced pressure divided by temperature to the fourth. And what you can see here is that we need to also include some mesonic contributions to get a good match with the lattice results. Because in our model, when we determine the grand canonical potential, what we use is only the fermionic quantum fluctuations, and we consider mesons only at 3 level. So we need to add these basically by hand here. But then we get a good agreement here as well. So here are also some other figures with comparisons. On the left, you can see the scale interaction measure, so the deviation from a non-interacting case. And on the right, you can see the speed of sound squared as a function of temperature. All right. So, but what we are interested in is the extrapolation of this model to finite density and low temperature. So what we need to do, first of all, we have to introduce an additional, so not just one, but actually 3 additional vector condensates. And also we need to solve the model in beta equilibrium and add the electrons to it. Then we need also a charge neutrality condition, and this leaves us with 6 equations, 5 of which are the field equations, and well, the Polyakov loop variables do not give a contribution here, so those are omitted in this case. Also, going to hybrid stars, we should have a hadronic crust and an outer core. So at low densities, we use the hadronic equations of state. we choose the SFHO and DD2 equations of state to.
About 5 minutes, Janos. Thank you.
All right, thank you. As representative equations of state, then to concatenate the quark and hadronic equations of state, we apply a smooth crossover between the two phases, for which we use an interpolation method introduced by Masuda et al. Which is an interpolation between the energy density, I mean the number density versus energy density curves, and this is basically an exponential interpolation, which like suppresses the quark contribution at low densities and the hadronic contribution at high densities. This has two parameters: the place of the phase transition and the width. So all in all, we are left with 4 tunable parameters altogether. So the sigma meson mass and the vector coupling, which are from the quark model, which are parameters that are not constrained that well, and the 2 parameters of the phase transition. Then we can constrain these from astrophysical measurements. So for example, the NISO measurements and also gravitational wave measurements. And now let me briefly show you some results. So first of all, we investigated the effect of the phase transition construction on the mass radius relations. And the question was that, are there maybe properties that do not change significantly by changing only the way we concatenate the equations of state? And this is what you can see on the right-hand side, which are with the SFHO equations of state. What you can see here is that the radii are quite dependent on the way we do the phase transition. But we found that the maximum mass is actually only weakly dependent on the concatenation method. And we also investigated what happens with different types of interpolations. For example, we also investigated what happens if we use a pressure versus a chemical potential interpolation, so a polynomial interpolation that was already mentioned by Professor Grant Matthews, and which was introduced in Gordon Bay et al. Paper. And we also investigated what happens if we use, instead of the SFHO equation of state, DD2 equation of state. And we found that it affects this maximum mass, but it remains approximately the same for these as well. Then moving forward, we trying to find the parameters that are the most compatible with observation using Bayesian analysis. And this is what is shown on the figure on the right. So the green contours here are the NISO measurements, and the red bar on the right is the radius constraint deduced from GW 170817 by Emily and Nala and others. And we did not use any upper mass constraints. And what we get here is, first of all, that the astrophysical data prefers lower sigma meson masses. And then if we only consider the 2 NISO measurements, then we get a vector coupling of around 4. Well, if we also consider the gravitational wave data, then we get a vector coupling of around 5. The interesting thing is that we can also try to estimate this vector coupling using meson masses also, so vacuum phenomenology, in a self-consistent approximation where the mesonic fluctuations are also considered. And from that, we seem to also get a vector coupling of around 5. And well, the phase transition in our case happens at around 3 or 4 times saturation density. All right, and these are our findings so far. And with this, I would like to thank you for your attention, and I'm open for questions.
Thank you very much, Janos. That was excellent. So, any questions? I have a quick question. Can you tell me a little bit about what the distinction is between your model and the sort of Polyakov NGL models I see?
Right, in the Polyakov, I mean, the NGL models, we do not have separately mesonic fields, but the fields that are responsible for the mesons are also produced by the quark fields, the expectation values of the quark fields, as far as I can tell.
Sure. Okay, yeah, that sounds. Okay, do you want to go ahead and stop sharing and we'll move to the next speaker?
Yeah, sure.
And then just for the slides, but any final questions for Janos? Elias, go ahead and share. Okay, well, in attempting to correct my error of letting the schedule drag on a little bit, let's go ahead and proceed. Thank you, Janos, again. Elias Elias Most will talk about projecting the likely importance of weak interaction-driven bulk viscosity in neutron star mergers. And I will give you a 5-minute warning. Thank you very much.
Thank you, Andrew, for the kind introduction. And thank you all for having me. I'd like to present some recent results that we've obtained in the context of looking into a new phenomenon associated with weak interactions and neutron star mergers that could potentially affect the post-merger gravitational wave emission and would maybe have small impacts on the in-spiral. It's not just work that I did by myself, that's work with a long list of collaborators, all listed on this slide. And if you want to have any more details, please feel free to reach out to me or just to go to our recent paper on the archive. So what's the general context that we find ourselves in? If we look at the gravitational wave event, then there are different windows that we could have into the system. We could, for example, look at the electromagnetic counterparts. But something that we've heard time and time again during this workshop is that the post-merger gravitational wave signal contains interesting imprints of high density matter. And that's simply because after the two stars touch and collide, you reach high densities, high temperatures, densities several times saturation. And so those are an ideal probe. And that in some form gets imprinted in the gravitational wave signal. And the way we believe in the future to be able to extract this is by looking at the frequency spectrum. And the way to think about this is very much like thinking about spectral lines of elements. So if you look at the sun and you look at the chromosphere, different elements will give you different line spectra. And there, of course, you can do experiments on Earth and then compare which one you have. Here, we can only do numerical simulations to explore this, but in principle, it's the same thing. And those spectra are typically characterized by having several frequency peaks. You can label them F1, F2, F3. Sometimes the F2 is called the F peak, but it doesn't matter. If you compare those spectra for different equations of state, they're different. And so that's kind of the thing you want to use. But there are certain uncertainties that come with doing that identification. Because ideally what we have seen, for example, in Ariel's talk earlier today, that these quasi-universal relations trying to relate high density property of high density matter in the post-merger spectrum to properties of low density matter in terms of, say, compactness. Some people use the radii of 1.4, 1.6, 1.8 solar mass stars, or here in terms of the tidal deformability. But then you could have corrections to that. And going back to the example of thinking about line spectra, if you think about the star that's moving away from you, you could have a Doppler shift. In the same way, people have suggested if you have finite temperature effects, they could also shift the or the appearance of quarks in that case of the earlier talk. They could also shift the frequency spectrum, and that's something that has to be accounted for. It's one of has to go into your error budget whenever you want to use those quasi-universal relations. We also did similar work a few years back where we looked into the dynamical appearance of quarks at finite temperature, and you could see that that causes a linear dephasing in the waveform. Just if you want to have a picture, what is actually causing that shift at finite temperatures, and that's something that potentially you then have to take into account. And the effect that I want to explore today is because they're not just new exotic particles like hyperons or quarks, but you also have copious neutrinos around. And once you push those neutrinos out of beta equilibrium, interesting things can happen because the system wants to restore itself. And so those gradients that go out of equilibrium might kind of produce something that looks like an effective bulk viscosity, trying to push the system back, and that could then affect your post-merger gravitational wave signal. And just to already set the stage, what that effectively means is that your pressure will get a correction, and the correction, if you adopt Navier-Stokes or whatever formulation is out there, will be proportional to the compression times some number. But I go into the details over the next slide, just so that we're all on the same page and get some impression of how that should work. And so what is bulk viscosity? If we encounter this, you can actually encounter it right now when I'm talking to you, because sound waves are compressional waves. And what that means is that when the sound wave is compressing and the air is expanding again, if there's a certain viscosity, then you will produce part of the energy in the sound wave, convert that into heat. In other words, if you look at the dispersion relation for a sound wave, you can see that there's a real part that propagates at the sound speed, but then there's a dissipative part, and the dissipative part is proportional to the bulk viscosity zeta. And so then if you have such a signal, this will be damped over time according to the value of the bulk viscosity. And then we can not only talk about sound waves, because what we will talk about will be oscillating stars or post-merger oscillations, and that works exactly the same. Here, gravity is the restoring force. So if I perturb such a star, and I would assume that globally the star would have, let's say, one fixed value of a bulk viscosity zeta, then those oscillations would damp on a characteristic time scale. And using basically the very same dispersion relation for sound waves, it's very similar. You do get an expression for what the damping time looks like in terms of the sound speed and in terms of the frequency oscillation and the bulk viscosity. And using those expressions, what I'm trying to motivate a bit later on is because in the post-merger phase, when we form this very massive, very compact, hypermassive neutron star, the star effectively acts like a perturbed star, and those perturbations can be damped using an effective bulk viscosity caused by neutrinos. What I would like kind of to motivate is what is the expected order of that effect, and this is something that we should actually care about. And so, in order to do this, we actually have to look at some microphysical models for this. That has been investigated over the past years. There's been some interest, for example, here by Mark Alford and Stephen Harris, but there's also been other works also involving Mark Alford, but also Armen Zidrakian on this call and his former student Aris Haradunian looking at bulk viscosity in neutrino chat matter. But what all of those mechanisms have in common is that the bulk viscosity acts as sort of a resonant phenomenon. So if you look at the right, you see that there's a very strong temperature dependence. The bulk viscosity there, it's a logarithmic scale, varies by 10 orders of magnitude. So it really matters what the density is, what the temperature is. And that will then, if you look on the left at the relevant time scale, greatly say if the effect is expected to act on 20 millisecond time scale, 1 second time scale, 10 second time scale. So it's really very strongly dependent on the thermodynamic conditions. And so a priori, it's not clear if you actually meet those conditions or not until you actually take a simulation and you check what are the conditions that you encounter. And what we did is we used, or better say what Stephen provided us with, is he produced 3 prescriptions of the bulk viscosity for representative equation of state models. Effectively, those were chosen so as to have upper bound on the bulk viscosity. What would be the largest effect that we would potentially expect? You can strongly see here that there is this huge temperature dependence. For example, if you look at the red curves for the NRO equation of state, that's significantly higher at 1 MeV than, say, for the IUF equation of state. And overall, the bulk viscosity in those models for NPE matter reaches at most 10 to the 30 grams per centimeter second. And now we have to kind of put this in perspective, because I'm not sure how familiar we all are with what these numbers mean and how they compare, but I will walk you through this in the rest of the talk. And in order to kind of have, really answer the question, how large actually is large, we have to introduce kind of a measurement tool to say, well, what's actually the right scale to compare with. And it turns out if you look at your equations of hydrodynamics, so you take Newtonian Euler's equations and you rescale them. So you introduce characteristic scales for density, the velocity, and the length scale, rho, v, and L. But then the equations become effectively dimensionless and are only governed in terms of the inverse Reynolds number, which is this number over there. It's the ratio of the bulk viscosity to the velocity at the length scale. It's kind of comparing the viscous scale to the gradient scale present in your flow. To give you some idea of what that typically means, we're talking about bulk viscosity here, but this is usually used to characterize shear flows. In shear flows, the bulk viscosity then determines if you have a laminar flow, let's say for a very small Reynolds number, or if you have a turbulent flow with very, very small turbulent eddies at very large Reynolds number. So this really, you can use that as a measurement tool to say, well, is the viscosity important or is it not important? And we need to translate that expression to the relativistic context, because that's purely a Newtonian expression. And what you can show is we introduced something that we call the bulk viscous ratio. That's this relation between this viscous pressure correction to the energy and pressure context in your fluid. That's a local correction. You can evaluate that in the co-moving frame. In the Newtonian case, this would only reduce to basically this pressure correction over the local density. And then what you can show that in the Newtonian limit, this thing effectively reduces to the inverse Reynolds number times a velocity squared, which is the characteristic velocity of your fluid. Think of that as like roughly about being the sound speed in the case of the neutron star merger. And so with this tool, we can then go on and see what's the relevance of the viscosity, what's the expected relevance of the viscosity in neutron star mergers, both in the in-spiral and in the post-merger. And so the in-spiral I want to focus on first, because we know that basically the orbital decay will also exert stresses on the neutron stars. So the question is, if there was strong bulk viscosity present, would that actually affect the gravitational waveform? So we did a very simple back of the envelope estimate. If you look at the system consisting of two stars, you have an inward pointing velocity VR. That comes from gravitational wave emission. The stars are moving in this helical orbit then with orbital velocity v and an orbital scale r. You can actually just plug in the definition of pi. We go to, as typically done in post-Newtonian, to a flat space reference frame. And then you have that this thing goes like zeta VR over the orbital scale. Now we can plug in numbers. Orbital decay goes like 1 over orbital separation to the third power. Orbital velocity itself is typically used as post-Newtonian parameter, goes like the Keplerian velocity times the radius. So we just plug this in. And then we find that bulk viscosity would enter at a fourth post-Newtonian order. So this correction goes like velocity over c to the 8th power, which is a pretty high correction. If you want to put that in context, spin corrections would pop in at like third post-Newtonian order or 3.5 post-Newtonian order. And the tidal deformability that we also heard at some point, how that can be used to constrain the equation of state, that would enter at fifth post-Newtonian order, but it has a very large coefficient, and that's why it's relevant. So it's kind of out from the start a very small number to expect with. And then what we did is we plugged in some numbers. We said, okay, let's take a reasonable bulk viscosity. We said that for cold stars and the densities there was about 10 to the 28. That's what we got from nuclear models. You plug in those values and you find it's a small number that you're getting, like 7 times 10 to the minus 4. We even did some more sophisticated analysis trying to compare that to like how many orbits differences would make. But it turns out you would need bulk viscosities that are at least 3 to 5 orders larger in order to facilitate any meaningful effect. So likely the in-spiral, or at least what we've seen from LIGO, is pretty robust compared to those effects that if they were present. And so now let's turn to the post-merger. That's something we haven't observed in gravitational wave detections yet, but it's something that we expect to observe either with LIGO at design sensitivity or with third generation detectors. And there, as we have seen, interesting things can happen, like quark deconfinement, or hyperons, or all kinds of interesting physics that we would like to probe. And also, we could estimate, could this effect of the bulk viscosity occur? In order to do this, however, I said that the bulk viscosity is super resonant in terms of that it really depends on a very narrow range in temperature and density. And if you look at what the range in a merger is, that's using a simulation that I did with a quark phase transition. Actually, quark phase transition here doesn't matter. But if you look at the right, there's like the phase diagram, something similar to Abrial. What he has shown is like temperature and the density in units of saturation. And now you can see that during the merger, we start to dynamically populate this diagram, and we start to probe very high temperatures compared to the scale where bulk viscosity was active. So bulk viscosity was active at scales of like a few MeV, but here you see we populate regions of like 20, 30 MeV. So natural question is, well, if this was, so hot, why could this effect ever be present? That was what I thought over many years, actually, that it couldn't work. But it turns out that you really have to look very carefully what regions in the density are being probed. If you look, for example, at very high dense regions, then you see this is about 5 MeV, and that's like the right scale. So it really depends on where in the merger you're looking at the regions where bulk viscosity could be active. And so what actually bulk viscosity would do, I will show you in a second actually how that looks like, but let's first look at what would bulk viscosity affect, how would it affect the merger? And that's because after the two stars, they collide, they don't immediately form this fragment, but there is some oscillation going on where the two neutron star cores fuse into one. Think of that as like a big perturbed neutron star. And these oscillations are effectively being damped by gravitational wave emission. And what we did is we can in principle estimate how far the intrinsic damping already is, because so you think of this gravitational wave effect as like an intrinsic viscosity to the system. And so what we did is we looked at the radial separation of the stars. We tracked that during the post-merger oscillations, as you can see down here. And then we said, okay, if this was a damping, then the damping timescale of this is about 30 milliseconds. That's at least what we extracted from the simulation data. You can then use the expression for a single star and say, well, if we want to, in a simplified way, kind of associate a bulk viscosity with that, how large would that be, just to get an order of magnitude estimate? And it turns out that this would be 6 times 10 to the 28, which is exactly the range in which the other bulk viscosity is active. So kind of as a first check, we're kind of in the right range here. So really, if neutrino-driven bulk viscosity would be present in large parts of the star, it would affect the gravitational wave signal based on what we find. We can then also quantify this using our measurement tool. We can compute an inverse Reynolds number of the system, and we find that the Reynolds number is about 100, or the inverse Reynolds number is 10 to the minus 2. So that's kind of the reference scale to keep in mind for this effect. And now what we did is we took kind of a stock simulation of like what does a neutron star merger coalescence look like these days. This is using like 1.4 equal mass merger with Veronica Dexheimer's CMF equation of state. And then on the background of this ideal hydro simulation, so there was no viscosity dynamically included in the simulation, we evaluated those expressions to estimate what the contribution of the bulk viscosity would have been. And now the important thing to highlight here is that the regions at high density, where you see it's like 2 times saturation, those are pretty cold. And this is exactly the regions in which bulk viscosity could switch on. And so we painted on the bulk viscosity after the fact. And then what you see is that throughout large parts of the star, this is like for the first 3 milliseconds or so of the post-merger oscillations, we reach viscosities of up to 10 to the 29, 10 to the 30 grams per centimeter second, which is larger than the intrinsic viscosity that we estimated before. So that's kind of very encouraging in a way that even though the thing is hot, initially when you have those oscillations where viscosity makes a difference, it's actually switching on. You can nicely see this if you take the fluid elements and you kind of bin them according to temperature and density. You can really see that we nicely go into the resonance here, almost reaching 10 to the 30. And if you look at the left, this is binning them at the function of density, that this is kind of constant throughout a large density range. So really, viscosity switches on in large parts of the star. And then what we can finally do is we use our measurement tool again, this bulk viscous ratio, which is basically a generalization of the inverse Reynolds number. And we paint on the viscosity and we check, is that number, how large is the effect? And then what we see is that if we look at the maximum of this throughout the simulation, so this is really showing it to you in 2D, but also then we have some density weighted and some maximum time evolution series, just to kind of illustrate better what the effect is. That at merger, this thing presents like a 4% correction. And then over time, it kind of decays, but it remains steady and constant. And you might say, well, 4% is not a large number. You know, what are you claiming here? But the interesting and important point is that we have a reference scale. We have the intrinsic viscosity reference scale of the system, and that is what we need to compare to. It's not, we don't expect viscosity as kind of a correction to equilibrium to have 100% effect. And it turns out if you use this, this estimated scale from the gravitational waves to define what is the inviscid bulk viscous ratio, what's the intrinsic bulk viscous ratio of the system, that's of the order of 10 to the minus 3. And so if on average, say we modify, or we would modify with the bulk viscosity this thing by more than 10%, that's a sizable contribution. And so from our current analysis, it looks like that bulk viscosity switches on in large parts of the star, and it provides at least a 10% or more correction to the correct reference scale that we should be comparing to, which is very encouraging in the sense that this is something that really needs to be included and self-consistently being taken into account. And in order to kind of get a further idea, although I have to say this is slightly far-fetched, but still an interesting comparison, we took simulations of heavy ion collisions, because if you ask, well, what are the simulations under, the conditions of relativistic hydrodynamics where viscosity effects are important, then, well, it's relativistic heavy ion collisions. And we compared the maximum evolution, the evolution of the maximum value of the bulk viscous ratio to the same quantity computed for a comparable heavy ion collision, where comparable is really meant in very, very broad terms. And what you find is that at least within the error bounds of that simulation, you do get a very similar behavior, in the sense that here the oscillations are damped. In the other case, you have an expanding gas where the expansion is slowed down by the viscosity. And so we can take this at least as some very, very vague indication that comparing, that number of the bulk viscous ratio affects the heavy ion dynamics. Maybe it would also affect the neutron star merger dynamics. We just take that as a motivation, not saying there is a one-to-one proper comparison. But then what would we actually do? So if we wanted to model this, that's kind of the next step. That's something we haven't done yet, but it's something that at least we're thinking about. And for that, you would have to combine numerical relativity, you'd have to combine viscosity, and you would have to combine relativistic hydrodynamics. And there are various ways of doing this. For example, two things I could advertise here. One is first order hydrodynamics that was recently introduced a few years back by Giorgio Noronha, Marcello Disconzi, and Fabio Benfica, and it's being actively explored here in Princeton, especially by Alex Pania, Franz Pretorius, and an upcoming study also myself. And there's also a new thing I want to advertise a bit, which we call iso-viscohydrodynamics, which George Noronha and I have developed, which tries to, in a more suitable way for astrophysical fluid dynamics, include those effects, and that would be suitable then for all kinds of viscous or systems affected by viscosity, either black hole accretion or neutron star mergers. And so just to give you some simple impression, we developed those new set of equations and we ran a few simple tests. That's, for example, is a blast wave test where you can actually see how bulk viscosity is affecting the shock front that we form here, how it's dampening this out compared to the perfect fluid case. But we can not only do this, we can actually also include effects such as heat conduction, where you can really—
About 5 minutes if you can. Thank you.
I only need 2 minutes, so no worries.
Oh, okay, wonderful. Thank you. Sorry.
So for the heat conduction, you can actually see that the heat conduction can either be slow, it can also be parabolic, that's more like the heat equation, or you can really get a wave-like character, so we can capture all of those effects. And the most interesting thing is actually when you look at, say, shear viscous driven instabilities, is not the focus of this talk, but it's some really, really important focus if you think about black hole accretion, or if you think about long-term evolutions of like neutron star disks or neutron star merger remnants. Then one of the main problems that you have is that if you run an ideal code without resolving the shear viscous scale, you're going to get smaller and smaller eddies as you change your numerical resolution. So your simulation results would never converge. And now the thing is, when we use this new iso viscosity scheme, we can actually perfectly resolve the viscous scale that we introduce. It's perfectly stable. And because it's using an implicit method, we can perfectly capture all kinds of strong discontinuities that are being present. This is something that we will be reporting on the archive pretty shortly, I think. And so to summarize, I hope I could convince you that beyond just looking at equilibrium dynamics effects, such as the equation of state or varying the equation of state, there could be other transport effects, such as bulk viscosity caused by going out of weak equilibrium. And those need to be explored, not just together with neutron star simulations, but they will also have a crucial dependence on the temperatures and densities being reached in the merger. So that's something that you don't expect to generically switch on, but you would expect that to switch on for specific families of equations of state where the temperatures are not too high, but the densities are also not too high. And the masses then of the stars can also only be in a certain range. So it's something that is relevant, but not across the entire range. But in order to really quantify what the effect would be and how fast the post-merger damping would set in, we would really need to do self-consistent simulations, because that was what all I was presenting was just like a simple estimate. But I think it's worthwhile to think about this given on what we have found. So with that, thanks a lot for your attention.
Wonderful. Thank you, Elias. Okay, so I didn't see who was first, but let's start with Armin Sadrakian, and then we'll go to Mikhail.
So yes, thank you for the nice talk. So how your result changed the basic perception that bulk viscosity is unimportant once you go to high temperatures above the neutrino trapping temperature 5 MeV? And because you are talking about pretty high temperatures like 20, 30 MeV, and in our estimates show that bulk viscosity is unimportant in this temperature range, exactly where neutrinos are trapped. So are you saying that this conclusion should be revised?
Basically, I'm fully there with you. That's what I thought for many years after talking with Mark about this. But if you look at this one here at the top row of that panel, that's showing you the temperature evolution in a merger. And in green, you see density contours in units of nuclear saturation. And the surprising thing is, although you reach high temperatures, you don't immediately reach them in the entire collision. You only reach them at the merger interface. But there where you have high densities, so what is sourcing your gravitational wave emission, that stuff is cold. And this is why when we evaluate the neutrino bulk viscous rates, although they are in the free streaming limit here, I have to add that, then you see that they switch on in the entire cold part, but not in the hot part, as you say. So the crucial thing is, yes, the temperatures are hot, but they're only reached in a small fraction of the remnant. And the rest of the remnant, where it's important, it's still cold. And this is because why they can switch on.
Okay, thank you.
Okay, Mikhail Chabanov.
Hi, Elias. Thank you very much.
Hi, Michi.
Nice talk. So I have a simple question. You showed in the previous slides that the bulk viscosity was frequency independent, so that it's a resonant phenomena. So how did you calculate that frequency when evaluating essentially the viscous tensor on the simulation slides?
I mean, what we assumed here for simplicity is we fixed the frequency to be 1 kilohertz. And the reason why we fixed 1 kilohertz was because in the gravitational wave signal or not in the gravitational wave signal, in the oscillations and the post-merger oscillations that we extracted, it's pretty much 1 kilohertz. So this is how we motivated that. But you have a good point in a way as to asking, well, is the global oscillation frequency the same as the local one that you would have? And for that, if you wanted to include that self-consistently, you would need to do better in terms of using some sort of local estimate for that. That is correct.
Okay, and then Elias, can you stop sharing? Jim, go ahead
Sure.
and share yours, and then we'll have one last question from Zidulin.
Very interesting talk. So, yeah, I'm just wondering, okay, so in the real world, when we are, for example, when we have already observed this damping effect.
Hey, Chris, this is Adriana. Do you have a minute? Just want to ask you this issue with the CS.
Sorry, Zidu, continue.
Okay, so how can we make sure that, I mean, how much damping effect is contributed by the bulk viscosity? So in other words, so is there a model independent way to measure this bulk viscosity when we really observe the damping effect?
So effectively, what you would do, we have been thinking a lot about that for the in-spiral if it was active. So the thing that you would have to do is for the in-spiral, for example, the bulk viscosity would remove energy from the orbit and cause a phase shift. So you would, like the tidal deformability, you would add that to the total budget of your gravitational wave phase, and then you would run a Bayesian analysis to see would that be relevant or not. For the post-merger, I think what you would have to do is, the problem is there's some degeneracy with the equation of state, but for every equation of state, you could basically check, is there an effect or is there not an effect, and then quantify what the imprints on the model is. There have been attempts to build post-merger gravitational wave models analytically, and you basically run those and then do a similar Bayesian analysis to extract if there would be a non-zero contribution or not. It's a very vague thing that I'm trying to say here, but I hope the general picture is clear.
Okay, thank you very much, Elias. We'll continue discussion on this tomorrow. Thank you very much, Jim, for your patience. So Jim Latimer, I'm very excited. We'll talk about symmetry energy constraints from theory and experiment.
Okay, thank you. I thank the organizers for inviting me to present some thoughts. I will like to discuss the recent results on nuclear experiments and their relation to the nuclear symmetry energy. And I would like to acknowledge generous funding support from various agencies, and also my excellent collaborators over the last few years, most of which are listed here. The main topics I'd like to address are, just to be firm, define the nuclear symmetry energy, how it's related to neutron stars, constraints on the symmetry energy coming from experiments such as nuclear masses and dipole properties and neutron skins. Also want to talk about theoretical neutron matter calculations and their predictions for the symmetry parameters, and also unitary gas considerations. And then finally try to make a summary of what I think the current state of the art, current state of understanding is, and what future experiments can hope to help with. So as we all know, the neutron star structure is controlled by the Tolman-Oppenheimer-Volkoff equations. They relate the pressure and energy density of matter, shown in a schematic equation of state on the left, and beginning with a point at a particular central density and energy, and integrating to the surface, we end up with a mass radius point. And as we vary the central energy and pressure, we can generate the entire mass radius curve. The two notable characteristics of this curve are, first of all, that there's a maximum mass, and that mass from experiment we know is of order 2 solar masses, give or take a few tenths of a solar mass. And because it's so large, this means that there's a considerable portion of the mass radius curve that is fairly vertical, which means that most observable neutron stars should have a relatively small range of radii. Now, depending on the equation of state, of course, the mean value of this radius can vary significantly. But there is a connection now between nuclear experiments and neutron star radii. If we look in particular at 1.4 solar mass stars, I noticed with Prakash some time ago that there was a high degree of correlation between the pressure of matter around the nuclear saturation density. Here we show examples between 1 times the saturation density and twice the nuclear saturation density. And the correlation is such that the radius varies roughly as the pressure to the 1/4 power, so that if you multiply radius times pressure to the -1/4 and look at very different equations of state that predict radii of 1.4 solar mass stars ranging from 9 kilometers to nearly 16 kilometers. Of course, a lot of these equations of state have since been ruled out, but in any event, there's a very general result that emerges that especially as we go just above the nuclear saturation density, there's a increasing degree of correlation, which basically peaks at around twice the saturation density. And the uncertainty is quite small. There's 2 colors on here, the black points and the red points combined are the original points we discussed. But later on with Yunwan Lim, we restricted the calculation to neutron stars of equations of state that could predict at least 1.9 solar mass neutron stars. So that eliminates several, the black points. And if we just look at the correlation implied by the red points, we get a pretty narrow range of values. And this has been pretty much validated over the years by various other calculations. But this is sort of the first relationship that emerged between nuclear matter properties and the explicit properties of neutron stars. And there have been several more that have been uncovered over the years. But the important point is that the pressure of matter, which is the fundamental thing we're looking at now, is controlled mostly by the nuclear symmetry energy. And we define the nuclear symmetry energy as the difference between the energies of pure neutron matter and symmetric matter, X being the proton fraction here. Schematically, that's just this difference shown by the red arrow. We see that there's a density dependence to it. Here's the saturation density. And there's also uncertainties due to the various nuclear interactions. We do know from various calculations that it seems that the quadratic expansion in the symmetry seems to work very well all the way from pure neutron matter to symmetric matter. In other words, if we expand the energy of nuclear matter as a function of density in X and expand its proton in terms of its proton fraction, you can expand around symmetric matter. The lowest order term is, of course, a quadratic term, and we only need to keep this first order or the second order term. Other terms are relatively small. Furthermore, the second order term can be expanded in density around the saturation density, and those 2 main parameters are the symmetry energy at saturation, around 31 MeV, and the slope parameter, so-called L, which is in the neighborhood of 50 MeV. And as long as this quadratic expansion is valid, we can extrapolate then to pure neutron matter, and that's just then given in terms of the symmetry energy parameter and the bulk binding energy at saturation, value here around 16 MeV, and the pressure of matter at the saturation density of neutron matter is directly connected with this L parameter. Neutron stars are not pure neutron matter, but near the nuclear saturation density, the proton fraction is on the order of just a few percent, and the corrections to the pressure of matter compared to pure neutron matter are contained in this term, which is on the order of just a few percent. So for all practical purposes, neutron star radii are connected to the pressure of pure neutron matter. So to get some few definitions underway, we can write some energy expansions for symmetric matter and pure neutron matter in terms of these usual incompressibility and skewness parameters. In addition, the neutron matter has a slope parameter term, and the symmetry energy is just the difference of these two. And so the definition of K-sim is just Kn minus K1 half. As Bill pointed out a couple of days ago, there is uncertainty in the empirical saturation parameters. So for this talk, we will consider saturation density as being 0.155 with a few percent uncertainty, binding energy with several percent uncertainty, and the incompressibility parameter with about a 10% uncertainty. Several of these higher order parameters, the rest of the higher order parameters turned out to have a high degree of correlation with the slope parameter. So studies, for example, of 261 nuclear interactions led to these correlations, which we will find useful to implement in the following discussions. So the first point I want to make is that nuclear masses provide probably the greatest reliable indicator of the nuclear symmetry parameters. It's quite obvious, especially if we look at it in terms of the liquid drop model, the symmetry energy of a nucleus is basically controlled by the volume and surface symmetry parameters, which are related by factor of a to the 1/3, and they're proportional, of course, to the neutron excess of the nucleus squared. But because we have this more or less linear relationship among the parameters, it implies that when we extract the nuclear symmetry energy from nuclear masses, that we'll find a linear correlation between them. And that's shown here. The correlation between SS and SV is quite significant. This comes from a study using the liquid droplet model, fitting couple thousand of measured nuclear masses. And the parameters of this confidence ellipse are actually independent of the symmetry parameters themselves. They're dependent only on the properties of the nuclei that we're measuring, namely their masses as A, an integer, and the neutron excess, I. And so forming these second derivatives, we can then establish the corresponding range in SV and the corresponding range in L, of SS for this correlation. We can also get the angle, the slope from these second derivatives, and we can get the degree of correlation, which is only about 3/1000 less than a perfect correlation. Now, it's known from studying models of nuclei that the surface symmetry parameter is very highly correlated with L and SV. So this linear correlation between SS and SV basically translates to a nearly linear correlation between L and SV. Here's an example by Cortelainen et al. Using the UNIDEF interaction and taking a typical uncertainty in a fiducial uncertainty in masses of about 1 MeV. We find that L is constrained between 20 and possibly 80 or so, but the degree of correlation with SV is quite high. Now we can also look at theoretical neutron matter studies, and chiral effective field theory allows systematic expansions of nuclear forces. And what's interesting about it is it provides the only known consistent framework currently for estimating uncertainties. So here's some recent results. There have been several groups that have looked at this. Driscoll et al. Give the pressure as a function of density and energy as a function of density. The 1 and 2 sigma uncertainties estimated self-consistently are shown as the dark blue and lighter blue bands. I will talk about unitary gas later. But you can see that even up to twice the saturation density, that the uncertainties are somewhat under control, and certainly at the saturation density, the uncertainties are quite small. Now, since the symmetry parameters are basically connected to the energy and pressure of pure neutron matter, we can, taking the correlated uncertainties between the energy and pressure, we can establish the corresponding uncertainties in L and SV coming from these neutron matter calculations. Now, there's actually two ways to do this. One is you can use neutron matter calculations to establish the neutron matter properties, and you can use symmetric matter N3LO calculations to establish the binding energy and the saturation density. The trouble is that pure neutron matters are more reliable than symmetric matter calculations at any given order. This is because symmetric matter is a delicate cancellation of short and intermediate range three-body interactions, which come in at lower than N3LO. But these are blocked, poly-blocked in pure neutron matter. So that makes neutron matter simpler to calculate and less subject to these three-body cancellations. So, and furthermore, the N3LO symmetric matter calculations aren't able yet to saturate within the empirical ranges for NS and B, for example. So instead, we take the empirical values for NS and B and then infer the symmetry parameters by simply using these relationships, and then include the appropriate uncertainties in the N3LO calculations of energy and pressure and the empirical uncertainties in the saturation density and the binding energy. And from that, we establish this correlation between L and SV. Now, related to this discussion, you see these curves that appear in these graphs coming from the so-called unitary gas conjecture. That conjecture is based on the fact that neutron matter energy is larger than that of the perfect unitary gas, which consists of fermions interacting via pairwise shortwave S-wave interactions with infinite scattering length and zero range. And cold atom experiments have showed us that they have a universal behavior, and with a measured energy that's proportional to the density to the 2/3 power, and a measurable energy from cold atom experiments consisting of this parameter 12.6 MeV for the energy at the saturation density. Now, the conjecture comes about from the fact that pure neutron matter should, if anything, be more repulsive than the unitary gas, because the scattering length is not infinite and the range is not exactly zero, it's small, but finite. In addition, there are three-body interactions which are generally repulsive as well. So the conjecture is that the energy of pure neutron matter should always be greater than the energy of a unitary gas. That's certainly true for the N3LO calculations as shown here. It doesn't apply to the pressure. It's violated below the saturation density. But the important point here is that the energy at every density is larger than that predicted by the unitary gas. So using that constraint, that the energy of neutron matter is greater than that of the unitary gas, one can establish a bounding region in the SVL diagram, where you have allowed regions and excluded regions. And I often like to joke that this must be more or less correct, because the Latimer-Swesty equation of state shows parameters that violate this conjecture, and should certainly have a modified symmetry energy parameters to be consistent with this. In any case, when we combine then the correlations from masses and N3LO, and I would argue that these are more or less independent correlations, one coming from empirical mass measurements of nuclei, the other coming from neutron matter theory. And we combine these two correlations, we get a very small range then of L and SV parameters that are consistent with both with both constraints. And the curves down here just show the correlation This has about a 6 MeV or 10 MeV uncertainty. Somehow it got left out there. Or 20 MeV uncertainty. Okay, so in comparison, if we other groups have looked at the symmetry parameter constraints coming from chiral EFT calculations where they use self-consistently pure neutron matter and symmetric nuclear matter interactions, and they predict a somewhat different correlation. And but I'm wary of this particular result because, again, the symmetric nuclear matter calculations cannot yet saturate within the empirical places for the saturation density and for the bulk binding energy. For future use, this shows neutron skin measurements of lead-208, 7 different results with their uncertainties, and the mean neutron skin measurement is between 0.16 and about 0.19 if we take the error-weighted average of these measurements. And we will see that that basically implies an L for neutron skins. The weighted mean gives us an estimated L parameter between 40 and 60. So the neutron skin is an important nuclear observable if we can measure it precisely, because it's directly related to, it's more directly related to the L parameter than other nuclear observables. So the difference between the mean neutron and proton radii, according to liquid droplet model, is directly proportional to SS over SV. We see that this has a high degree of correlation with L. And in fact, Brown found a while ago that the correlation between the neutron skin and the symmetry energy was most simply stated in terms of a direct proportionality that existed between the neutron skin and the derivative of the energy, which we can write as this L twiddle parameter function. So L is the value of L twiddle at the saturation density.
About 5 minutes.
Excuse me?
Yeah. About 5 minutes, thank you.
Okay, so at 2/3 of saturation density, then that's where the highest degree of correlation is between R and the slope. And since we can expand the symmetry energy in terms of SV and L, we basically get a linear correlation between SV and L, and which is basically the same thing. So Fernstall several years ago compiled calculations of the neutron skin thickness from a wide variety of relativistic mean field and skirm forces. And here we can see the almost perfect correlation between RNP and the L parameter itself. There's a slight degree of curvature because the best correlation would be at the value of L twiddle at 2/3 the saturation density. There's also a nearly linear correlation between the skin thickness and SV, and this implies a correlation between L and SV that, again, is close to but not quite linear. So this has been revisited in the last year by Reed et al. And by Reinhardt et al., who have taken, again, a different variety of nuclear forces that are somewhat better constrained to nuclear properties, and they give higher correlations between L and SV than the Fernstall compilation does. But basically the slope is the same, and they're all more or less consistent with each other. The slope we get from nuclear masses is shown by the dashed line. The slope we get from the N3LO is shown by the solid line. Now, if we take the recent Prex measurement of the neutron skin thickness, as announced, is 2.28 Fermis plus or minus about 0.07 Fermis. These different correlations between L and SV and the neutron skin thickness basically give us these ranges of the L and SV parameters coming from that measurement alone. So there's no information here from nuclear neutron matter studies or from nuclear masses directly, but these come from the just comparing the results of these force calculations with the neutron skin measurement. And although it has been stated that there is some tension between the Prex measurement of the neutron skin thickness and the parameters around 50 MeV that we would get from looking at nuclear masses and neutron matter studies, you can see that to 1 sigma, which is shown by this first curve here, that actually that the traditional range of symmetry parameters, even independent of which kind of interactions results you use from Reinhard, Reed, or Fernstall, to 1 sigma there is overlap here. So at first glance, one could not say that there's the tension is that extreme between the Prex results and traditional studies, even though the difference seems quite large, over 50 MeV. And that's basically because the large size of this of the 1 sigma region here is driven completely by the uncertainty in the Prex result of 25% in the neutron skin. So if we take the Prex result and combine it with that for masses and N3LO, it barely changes the result we get from just masses in neutron matter studies. And we get a result around 50 MeV plus or minus 10, and L plus or minus about 1 in SV. We can also look at the electric dipole polarizability. There's important correlations between the polarizability multiplied by SV and the neutron skin thickness. In fact, this correlation is quite good, as Rocca-Mazza showed. He used the liquid droplet model basically to justify this particular correlation. And for 3 important nuclei, namely tin-120, lead-208, and calcium-48, there have been recent measurements of this dipole polarizability. So if we look at this for tin-120, the Rocca-Mazza correlation using the measured value of alpha SD basically predicts this linear correlation between alpha SD times SV and the neutron skin thickness. And this band shows the experimental uncertainty then in the measurement of alpha SD. There have been 3 measurements of the neutron skin thickness of tin-120, which is shown in red, extending over this wide range, in green over this narrower range, and then in blue over this even smaller range. If you take the weighted mean of those 3 measurements, you get the distance between these 2 thick black lines. And the uncertainty in alpha D translates into an uncertainty in SV. For example, if SV is fixed at 30, then basically the uncertainty in alpha SD is about 1 MeV, leads to 1 MeV uncertainty in SV. So you can see that the overlap of these predicts an SV value between mid-20s and nearly 40. So unfortunately, the measurement of neutron skin thickness in alpha D in tin is not yet sufficient to constrain the symmetry parameters more, although it gives us a result consistent with what we had gotten already. We do better when we look at lead-208. If we take the several measurements of the thickness of lead-208 that we have so far, that's between about 0.16 and 0.19 Fermis, and the correlation from alpha that Rocca-Mazza found for lead-208 is shown in blue, and Pia Karowitz and Reinhard have recently revisited that and established slightly different correlations, but they're all more or less consistent with each other. The Prex measurement, on the other hand, is shown over here, and you can now begin to see that there is tension between the Prex measurement of the neutron skin thickness, and that what would be predicted by the dipole polarizability measurement of lead-208. And finally, we can look at
close.
Yep, this is the last slide. So basically, so we look forward to upcoming measurements that CREX is going to make of the skin thickness of calcium-48. The skin thickness of calcium-48 from all these different theoretical calculations is roughly the same as that on lead-208, in spite of the fact that it's a much smaller nucleus. It's not exactly a linear correlation, and the slope isn't 1, but it's not far from that. The experimental measurements of lead-208 are shown between these dashed lines, and the skin thickness of calcium-48 will then go a long way to helping us unfold this. But we also have the dipole polarizability of calcium-48. The experimental measurement is shown here, and these are various ab initio and theoretical calculations of it as well. So the Prex 208 measurement of skin thickness suggests that the calcium-48 thickness should be larger, basically, than most theoretical calculations so far. So we expect to see tension then between the Crex result and the Prex results, but we'll wait till October to see that. And if the Crex results are consistent with Prex, then it means we are going to have to explore things, I think, a bit further. So here's my summary, which I'll basically just leave up. But the bottom line is that the current neutron skin and alpha D measurements from these nuclei at present are too uncertain to yet significantly constrain further SVNL that I think we have a good handle on from masses and neutron matter studies. And the upcoming Crex measurements will be very enlightening. Okay, well, thank you.
Wonderful. Thank you. Thank you so much, Jim. Chuck has a question.
So Jim, just a comment, since you quoted results for neutron skins in lead and calcium, or excuse me, and tin, but never explained them. Those results are potentially model dependent.
Oh, yeah, I left that. It's a short talk. So, of course, all both the theoretical calculations have model dependence, and the experimental measurements have systematic uncertainties as well. One notable advantage that Prex and presumably CREX will have is that model dependence, the systematic uncertainties seem to be under somewhat better control. But I think if you talk to the other experimentalists, they might disagree with you a bit on that subject. But but you are right. There are systematic uncertainties here. The present uncertainty in the Prex measurement being 25%, that doesn't necessarily put it at that severe difference from the other measurements, which are basically averaged within this range here. Does that
systematic errors in the other measurements are potentially larger because of the strong interactions, and so it's true. PREX has systematic errors, but the strong interactions are under much better control.
Yeah, so I think the systematic uncertainties in the Prex measurement are largely coming from counting statistics. Would you agree? That's the largest source of uncertainty?
Yes, we're dominated by the statistical error.
Right. Okay, and to be fair, the other experimental measurements, I don't think have done a detailed analysis of their systematic uncertainties, which could very well be larger than their quoted experimental uncertainties. So this band here might be considerably wider than I've got. This is just using published results. So that's a fair statement you've made, yes.
Okay, great. Other questions or? Armin, I see your box is yellow.
Oh, okay. Maybe I can ask a question. Hi, Jim. Are there any constraints to higher order these characteristics of this expansion? You mentioned skewness and
right. So,
but you focused on this too.
The
right.
best correlations that I'm aware of are ones that I summarized in the unitary gas conjecture paper with Ingo Tooze as the lead author, in which we looked at several hundred non-relativistic and relativistic interactions, and basically threw away those interactions that did not really satisfy what are believed to be good, having good binding energies and saturation properties. And of the remaining 261 interactions, these correlations appear with with correlations on the order of 90% or so. And relatively, I mean, the uncertainties are not tiny, but they're not grossly large either. So there's no direct experimental measurements of these quantities in particular, but the correlations arise from nuclear interactions that predict these values. And then when you fit those interactions to charge radii, binding energies, etc., the ones that do a good job of fitting nuclei have these embedded correlations built in. But of course, some of those correlations could be systematic simply because a Skirm interaction, for example, is a power law expansion. And since these come from power law expansions in the density, the Skirm interactions are power law expansions in the wave number, but you would expect some correlations among these parameters simply because of the fact that the Skirm interactions themselves are expansions.
Okay, thank you.
Oh, Vim, please go ahead. You're still muted, I think.
Yeah,
there we
it
are.
should be better now. I have just a brief comment about the dipole polarizability from a theoretical point of view. Anything that is done with mean field is questionable, even if it agrees with measurements, doesn't really mean all that much. And ab initio work has always encountered great difficulties in describing the giant dipole. So I think the theoretical correlation is wonderful, but I think there is still much work to be done there.
Okay, I'm not an expert in dipole polarizabilities and how they're extracted and the systematics you're discussing, but you're certainly right. Yes. It's a good study. It's a good venue for future studies, though. I think you would agree.
Yeah, I totally agree, and I would really like to see response functions of the dipole type that compare the complete response, so that one can have some confidence in the correct theoretical interpretation of these results.
I think there's also some uncertainty because some of the dipole strength is in these pygmy dipole resonances.
Exactly.
So.
Okay, great. Anything else before we conclude the session for today? Well, I just want to say thank you very much to Jim and all the other speakers. Thank you for your patience with the schedule. I think they were wonderful talks.
Okay. Well, goodbye, everybody.
Oh, wait. I see one hand up. Is that?
Oh.
Wait, I see two
No, it's
hands.
just me clapping.
Oh, that's clapping. Yes, of course.
Okay.
Chris. Okay, great, Chris. Do we need to do anything else? Or we good?